Okay, we're back for part two of the describing functions video. We're on to the lesson, so back to the sheet of paper. We see the expectations, compare and contrast the properties of various functions and ways to describe functions, and we'll go back and forth to the notes over here when we come to them. Um, Domain and range, of course, we talk about the domain and range of a function, and you've been doing that since grade 11. Asymptotes or discontinuities. We can describe uh, a function in terms if it has an asymptote or it has a discontinuity. Um, in the note here, a function is continuous if there are no holes or breaks in the graph. A graph has a discontinuity if there is a hole, break, or jump in the graph. And we talked about that when we were doing our sorts, that discontinuity is if you have to lift your pencil when you're tracing along. Um, and so we have to mention those when we're describing graphs. X and Y intercepts, remember the x-intercept is when y is 0, and y-intercept is when x is 0, and remember that from grade 11, right? That's the y-intercept, and that happens when x is 0. This is the x-intercept, and that happens when y is 0, right? So that's how we get x and y-intercepts, and that's going to be one of the things that we're interested in all year is finding x and y-intercepts. Intervals of decrease and increase. And we talked about this a little bit, but decreasing means that the y values are going down. Increasing means the y values are going up. Exactly how we would generally think of it. We read a graph from left to right, and if it's going up, it's increasing. If the graph is going down to the down and to the right, then it's decreasing as we read it left to right. We'll make these definitions a little bit clearer if and when you take calculus. But for now, going up and going down is good enough for us. An interval of increase states the x values where the graph is going up. So we're not interested in what the y values are. We're interested in the x values where the graph is increasing or decreasing. Symmetry. We talked about symmetry, and we'll spend some time determining some symmetry of functions. A function can be even, odd, or neither, and the bonus was, remember, to see if you could find a function that was both even or odd, or if such a thing exists. Geometrically, an even is when it's symmetric in the y-axis, but there's also some algebra that goes with it. Similarly, odd is symmetric through the origin, or flips in both axes, and that's the algebra that's involved. Um, and a function could be neither. So for instance, the exponential function is neither even nor odd because it's not symmetric in the y-axis, and it's not symmetric through the origin. So this is not that one is neither even nor odd. End behavior, we'll spend quite a bunch of time speaking about end behavior when we talk about polynomial functions next chapter, but the idea is where are the starts and ends? So for some graph, we talked about as x is way out here in the negative, it starts. Where did the output go? Is the output up high or low, or what's the story? And same thing is on this side. How does it end? On the right. So as x goes to positive infinity way out this side, where is it going? Is there an asymptote, or does it go up to positive infinity or negative infinity, and so on? Maximum and minimum points is a way that we'll describe graphs, and we'll talk about turning points, the idea of a turning point of a parabola. Well, it's got a turning point. It's got a minimum at the origin right there. That graph has a minimum. So that's what we mean by turning points, is where it starts going the other way. It was decreasing, then it turns and starts increasing. And we can describe graphs in all these ways. Now, the first example, I'm not going to do all of them. You're actually going to, a big part of your homework is to go through this stuff for all of them, but I'm just going to do the middle one. The domain and range. The domain, remember, are all the x values where it's defined, and there it is right there. The domain is x has got to be greater than or equal to 0, and the range, of course, is the y values. So here and up, and this is the little card. Don't draw on your cards. That wouldn't make any sense to do that. But the range is y is greater than or equal to 0. Discontinuity. Asymptotes, I can see there's no asymptotes, but it's discontinuous for any values less than or equal to 0. At 0, I can kind of put my point down, but we'll say it's continuous only on its domain, right? On x has got to be greater than 0. In fact, even though we won't worry too much about this, we can say that it's discontinuous at x equals 0 and to the left. It's kind of like the smoothness. It needs to be smooth, and it's not smooth right on its endpoint. But that's a little bit being a little bit picky. Discontinuous on x is less than or equal to 0. Intervals of increase and decrease. Well, it's increasing on, and I'm going to go to interval notation here. It's increasing on everything besides at 0. It's defined at 0, but it's not really increasing at 0, is it? And that's, it's kind of a minimum there, isn't it? 0 to infinity. And it's decreasing nowhere. Symmetry, even, odd, or neither. Well, this we'll have to get more practice at, but is this symmetric at all? It's not even because there's no graph on the other side of the y-axis. This is neither. This one's neither. End behavior. Well, notice that it doesn't have an ending on the left, so I can't even talk about when x approaches negative infinity because it's not defined there. It's not part of the domain. But as x approaches positive infinity, what happens to the y values? Well, x goes way off to the right. What happens to the y values? They go to positive infinity as well. Slower, because it's kind of evening out, but it's going to go however high you want to go. Y will eventually get there. And that's, oh, sorry, minimum and maximum points. This has a minimum, doesn't it? Minimum of y equals 0 at x equals 0. No maximum, right? Because it keeps going for forever. And again, I'm skipping A and C because you're going to have to do it for the homework anyway. How are these two functions the same? And if you get those two cards in front of you, there's lots of ways that they're the same. There's intervals that they're both increasing. But I have to list a couple maybe. Both have a domain that's x is a member of the reals, right? Which means there's no restricted operation. I can find the sign of any input and I can square any input. So that's true for both. And let's come up with another one just for fun. They both have a point 0, 0, don't they? I can't say that this one has a minimum at 0, 0. This one does, but this one doesn't. But it still both contain that point. And if we thought harder, we could probably come up with some more. How are they different? Well, one is a parabola and one is a trig function. You could come up with that if you wanted to. If we just go with respect to our big list of stuff, we could talk about spots where they're not increasing or decreasing. But the main thing is that I want to mention is x squared is even. And g sine x is odd, right? If I look at the graph of sine x, where is it? It's got that idea of the double flip it down, flip it across. It's the same function, or through the origin, it's an odd function. And we'll be able to prove this later when we do our unit on trig functions. All right, last. No, not last, second last. Show that this function is even. So how can I show a function is even? I need to show, required to prove, that f at x equals f at minus x. This is what I want to show, right? Well, how am I going to show that? Well, I'm going to treat this kind of like a trig identity from last year. The left side is just f at x, which is just x squared plus 3, right? the right side must be equal to this somehow. So the right side is f at minus x. So what do I want to do here? I want to take out the x and put in minus x. Right? Take out the x and put in minus x. Well, negative x squared is negative x times negative x. So therefore, the left side is equal to the right side, and I've got f at x equals f at negative x. And as soon as I've shown that, I can say, therefore, f at x is even. Now we're asked to show that this other function is odd. So what's the required to prove or required to show is that g at x equals negative g at negative x. So how am I going to do that? Well, I'm going to break it into left and right side and see if I can manage this. G at x is just this function. The right side, negative g at negative x. Now, how I'm going to do this? Negative g, well, g is x cubed plus 4x. X cubed plus 4x. But notice this x is an x there. It's not just x, it's minus x. So this expression I've got to clean up. And if I'm going to show this as odd, this has to end up being like this. Now I've just got to be careful about my minuses. What's negative x cubed? Negative x times negative x times negative x is negative x cubed, right? Or negative 1x cubed. I guess I could think of it that way. 4 times negative x is negative 4x. Now I've got this minus out front that I'll distribute through x cubed plus 4x. And look, left side equals right side. Therefore, g at x equals negative g at negative x. Therefore, g is odd. And it's this sort of proof, by the way, folks, if you get the bonus question, I want you to prove to me that it's both even and odd using this technique. Just a note in passing, some textbooks use this as they're required to prove for an odd. Notice the minus, if I put it here, if I divide by negative 1, it's still the same expression. And so if you'd prefer that one for your required to prove, you can go right ahead and do that, but this is the way that I'll do it. A little bit tricky and detailed in here about the minuses, but just keep track of your minuses. The last example, and the reason why we do this is kind of mean, I get, not really mean, not mean, to sort of set you up that I'm going to do this example, then not do it. But one of the feedbacks we had from our university students returning, grad students from Northwestern, is that, you know, they have trouble learning to read from a textbook, and they need to, because part of their course is learning straight from a textbook, that their professors don't teach them all the material, that they're required to learn a lot on their own. And so I'm going to start doing this. Instead of doing this example, I want you to read this example in the textbooks. It's quite like this one, and then you're going to learn how to do this type of question on your own. What I will do, though, especially if you remind me, is I'll put a picture of my solution for this one, so in case you would like to try it, on the Facebook group, so you can check that one out. But learn that one from the textbook. Bunch of homework. Long lesson today, I realize, folks, but we'll get through it. It's a lot of small, quick stuff. So I think you'll have success once you get back to class. That's it.